In this video, I'll be talking about the electric field due to an electric dipole. So let's consider this is an electric dipole here. So this charge is the negative charge Q, and this is a positive charge Q. And these two charges are located at a distance. Let's say this is an origin here. This is an origin, and this is located at x equals to plus a, and this charge is located as equals to minus a. These two are at exactly the location, and we are interested in finding out the total field at this point P, which is at a distance y. We call this as an x-axis and this as a y-axis. Okay. So how do you find out the total field at this point? And this point P is right on the perpendicular bisector of this line. Due to this positive charge, the electric field is always away from the charge. So due to this positive charge, the electric field is away from this charge. So this is the direction. Let me make it to the red color. Okay, so this is the electric field due to the positive charge, and due to this negative charge, the electric field is always towards it. So this is the direction of the electric field. Okay, this is E, and this is also the E. As these two charges, this positive charge and the negative charge, have equal in magnitude, the magnitude of the electric field at this point due to both charges is exactly the same. Let's call this as an R, the distance R, and this is also an R. And we also call this angle as a theta, and this angle will also be theta. And you know that this distance is A and this distance is A. So now we're going to resolve the electric field into the two components. Okay, so first let's resolve this electric field here. This electric field can be resolved into two components, one along the x-axis. As this angle is theta, this angle will also be theta, and this component will be E cosine theta, and along the y-axis, or the y component, will be E sine theta. So here we have resolved the E sine theta. Now let's resolve this electric field vector. Okay, so this one can be again resolved into two components. As this angle is theta, this angle is also theta, and the electric field along the x-axis is E cosine theta, and along the y-axis it is E sine theta. So we have now resolved this electric field as well. So what you see is we have the two components E sine theta and E sine theta that are equal but opposite in direction. So these two cancels out themselves. So these two cancels out. So what does that mean? So there is no electric field along the y direction. The only electric field is only along the x component. So we have only x component. Okay, so now let's find out the total electric field. the total electric field is given by 2e cosine theta. And the 2 is because the one electric field is coming from the positive charge and the other is coming from the negative charges. So that's the reason e cosine theta, one from the positive charge and the other from the negative charge. That's why we have 2e cosine theta. So if we look into this triangle, so what's the cosine theta is? Let's find out first the cosine theta. The cosine theta. If you look here, the cosine theta is simply equal to a over r. The cosine theta is base divided by the hypotenuse, so a over r. And also the electric field E, the electric field E, or this E, due to this charge is given by k q over r square. Okay, that's by the definition. So now let's plug these two into this equation, into equation 2. What you get is 2, electric field is kq over r square, kq over r square, and cosine theta is a over r. That's the total electric field. Now let's further simplify this one. 2 kqa r squared times r. We have r squared here and this is r here, which then this will be equal to r cube. And also if you look into this triangle, what is r? R is simply equal to, from Pythagoras theorem, this is equal to a square plus y square. So I can write down this is a 2kqa, and if I take a cube of this one, it will be equal to a square plus y square 3 over 2. This is the E total field. All right. Okay. Let's call this equation number 3. Oops. So now let's further simplify this equation. We know now the dipole moment. The dipole moment, if you look at the dipole moment, the dipole moment is defined as the P, which is denoted by P, is defined as the Q times the distance between the two charges. In this case, the charge is Q and the distance between the two charges is, this distance is A, this distance is A. So the total distance is 2 times A. So our dipole moment will be QA times P. Now let's plug this equation 4 into equation 3. Into 3. So what you get is now E total electric field. You see now I can replace 2QA together by P. So what I will get is K times P divided by A square plus y square divided by over 3 over 2. All right. So this is now equation number 5. This is equation number 5. And now we can take a special cases now. Let's talk about some of the special cases. If this point P, now let's come back to here. If this point P is very, very far, much further, very, very far, okay? If this point P is very, 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 very far. If that is very, very far, then how can you write down? Well, point P, this is special case 1. Just long distance from the dipole. Then mathematically we can write down this when this y is much, much greater than a. So what is y? Y is this distance. When this y is much, much greater than the distance between the dipoles, or this point is very, very far from it, then when y is much, much greater than a, then y square plus a square is very, very close to y square. So what does that mean? Let's say you have y 10,000 and a 1. If you add them together, it is still close to 10,000. So we can approximate this, that the a is negligible in terms of y. That's what it means. And the idea of this one is, now this equation will be now simplified into another equation. So now let's use this number 6 to number 5. What you get now? E total is Kp, and we can replace a squared plus y squared by simply y squared. Y squared, and then we have 3 over 2 power. That means now Kp is equal to y cube. Now we got now an interesting equation here. So when the point P lies at a very long distance, then the electric field does not vary as a square. Now it varies as a cubic function. So in this case, electric field E varies as 1 over q. That means the electric field decays much more rapidly. Following 1 over by q equation, and it follows more rapidly in compared to a point charge. If you remember, the point charge varies as 1 over y square or 1 over r square. Okay, but in this case it varies as 1 over y cube. That's the reason I said it varies more rapidly. All right. Okay, now let's choose another case here. In this case, we assume a is equal to 0. What does that mean? When a is equal to 0, that means both charges, this negative charge and this positive charge, lies exactly at the same location. What does that mean? That means there is no any charges at all. Both positive charge and the negative charge lie exactly at the same location. That means there is no any dipole moment. So, or in other words, mathematically, when A is equal to 0, I can plug into this equation. I can plug into this equation or into this equation. So if you see, if A is 0, then the total electric field is 0, or the total dipole moment is 0, because if A is equal to 0, P is equal to 0, and if P equal to 0, then the total electric field is 0. So in this case, what we have, E total electric field is equal to 0, which makes sense because A equals to 0 means both charges, this charge and this charge, lie exactly at the same location, overlap each other, and this is positive charge and this is negative charge. That means there is no charge at all, and that's the reason we get the total electric field as 0. The third case we'll talk about is when Y is equal to 0. And what does that mean again? When Y is equal to 0, that means this point P lies right here, right in between. So you can now, how do we then solve it? Then we can just plug into this equation. When Y is equal to 0, when Y equals to 0, we will have simply A squared over 3 over 2. So in this case, what we have is E equals to 2K cube over A squared. Okay, so I'm just plugging Y equals to 0 into this equation. So now this one is, in this case, the electric field is simply equal to 2kq over A squared, which is, if you look at this one here, kq over A squared, this is the electric field due to one charge, as we have two charges. So if we look at this point, the electric field is in this direction due to the positive charge, and due to the negative charge, again the electric field is in this direction. So the total electric field is now doubled. That's the reason we're getting 2kq over A squared. So that's it from the electric field due to an electric dipole. If you have any question, please write down your comments